This paper addresses mental models used in learning. And to learn mental models, you need adaptation. Therefore, the network that we discussed will have adaptation of the mental models. But it also addresses the use of different mental models at the same time to switch between them. And to switch between them, you have this control that is applied from this metacognition perspective. So that means you have a lot of things. And let's start with the idea of metacognition. That is a form of cognition about cognition. And that means what people know about their own cognitive processes, how they put that knowledge into use in regulating these own cognitive processes and also the behavior. And when it's especially used for learning, sometimes also the word self-regulated learning is used. So in the learning, you use different mental models. That's that was the case that we study. In this case, in particular, that you use visualization to give some support to learning of a numerical or symbolic skill. And then the metacognitive control concerns the decision when you want to switch from one to the other mental model. So the background is that we use network-oriented modeling based on adaptive temporal causal networks. They are specified according to 3 types of characteristics. The first type is what you usually see in pictures of networks. That's the connectivity, where you specify what node is connected to what other node. And then you can also give the connections a weight so that they can have different strengths. But that's not the only thing, although pictures may lead to the belief that this is all for a network. And that is actually not really true, because if you don't specify how you use multiple connections to one node, how you combine them into one aggregated impact on that node, then the network is unspecified. So therefore, aggregation is another important type of characteristic, and that is specified by combination functions. See that you can be specified for any state Y separately. And as a third type of characteristic, we use timing characteristics. That's from the idea that states can change over time in different speeds. Some can be very slow and some can be very fast. That's what you see in applications. So if you would not take that into account, you would have an artificial type of synchrony between the states, what you don't want to have a good application. So then as part of that, I introduced the notion of self-model, and then you get a self-modeling network. That means a network with a self-model, where you can have the network structure characteristics, as I showed in my previous slide, like the connection rates, as additional states. So, for example, for such a connection rate, you introduce a state W that represents the value of that W, that omega. So that means that if you have to do the calculation, usually you take this as a parameter, and then you have a variable, and then you use that value to do the calculation. Now you use the value of this state in the network. That's just a node in the network. And similarly, you can do that for other types of characteristics, like the excitability threshold of a combination function. You can also add a state for that. So that's how you realize that parameters of your model become variables in your model. So that makes it easy to handle the adaptivity of these parameters, of these network characteristics. So that's a very easy and transparent way to introduce adaptivity for networks. You can also iterate this, that if you have done it once, then you have a new network, and then for that network you can also apply the same step, then you have higher levels or higher order networks or self-models. So the example that I use in this paper is just from the primary school, where children learn to do multiplication, And then, for example, you can multiply one number. These are numbers in that case. I represent now them by letters as variables, but for children they will always be specific numbers. So these numbers, if you do the addition here first and then the multiplication, then you have the same result if you do the multiplications and then the addition. And then exercises like that, they can try it out and find out whether or not that holds. So in this case, typically some detour via visualization can be used. It can consider two rectangles with the dimensions A and B and C. And then together they are the area of the big rectangle. So these rectangles together are the same area as the rectangle in that side. So by metacognitive control, it's determined when to switch from the numerical to the visual mental model, or in this case geometric. And that supports the learning of the numerical. So you can try to find it out in the numerical way, or you can just do it and then come back to the numerical side. So the model, the network model works like this. This is just a representation of the calculations you do in a numerical model. This is a product of the two. Here also a product of the two. And then the sum of the products. And this is the other one with the big side, the sum of the two, and then the product. And this is, in principle, a similar way of operating, but then with the geometry. So the numbers are here as the dimensions of the rectangles, and then you determine areas of these rectangles. So these are two different mental models, the numerical and the geometric mental model. So what can we do then? That's the switch between them. If you switch from one to the other, then you transfer the values. These are the numbers, and then you take that as dimensions there. That's the transfer from numerical to geometric, but you can also transfer back after you did some things here and you found out some areas, then you can transfer back. So these are things that you can control to switch from one to the other. Then you also have to do the transfer, and if you have to switch back, you also have to do the transfer back. So then I come to a next level where we have an explicit representation of the structure of the mental models. So, for example, this is a self-model, you can say, of this mental model. It represents the connection weights of this mental model. All arrows are represented by network states or nodes now. So that is the self-model of this mental model. This is another additional self-model, which is a kind of summary of how your skill is. That's not exactly this, but just determines based on that. And this one is a self-model for the transfer between the two mental models. Note that this model is not, the numerical model is represented explicitly so that it can learn. So these W's can change over time. That's how the learning is taking place. This model is assumed that it's already okay, that there is no learning needed, so therefore there is no such representation as here for that geometric model. But otherwise it could also have a similar representation here. So this is a level where you have the self-models of these mental models, and then we add another level, that's for the control of the choices for these mental models. And that's defined here. Here we have some monitoring of the skills. So these are remember the models that we have there. And here we have a second order self-model for the learning status. That is monitoring what is determined here. And then based on whether or not your skill is good for the numerical side or for the geometric side, you can make a decision what you want to do with the choice of your mental model. And that's what these states do. They make the choice for the different connections to become active, to let the transfer happen and to let this model work. So that's the total network. So we have the basic level where we have the mental models. Then we have a level where we can adapt the mental models, in particular here. So that's the adaptation level for the mental models. And then we have the control level where we can control these processes. So this is a simulation example. So here there is a switch to this is, for example, the area of the rectangle that is determined. So this is after a switch to the geometric mental model. And this is the numerical multiplication. You see that the numerical multiplication is after you found out how the area is of the rectangle. That means indeed you get this value of the numerical multiplication by using that geometric representation. So otherwise, if the numerical multiplication would have worked, that would not have been in this order, because the first step is always try the multiplication in this case. So then the total area comes, and this is the final answer, it comes here. And also here the geometric interpretation is done, and then the numerical. So that then you can see the different levels, the higher levels. You see that the learning in the numerical model starts to take place here, because you get this feedback from the geometric side. These are the decisions to switch, and that's because of this learning status of the numerical model is very low, so the learning skill is low here, and now it starts to increase with the increasing of this learning, and then it comes here, and then you see that this switch is not needed anymore at this point in time, because now the numerical model is already learning very well. So therefore that is just over after some time. So this is what I wanted to tell. So I wanted also to keep in the time, of course. Is there any question for the moment? No question?